Hey, students. I wanted to take a look at the homework problems that I had assigned last time. And we're going to be basically doing problems 1, problems 2, problem 3, and then problem 4 is the one I actually assigned for homework on your lab. And we'll get started. So let's just first on number 1 label things. This is the mass, this is the height, this is the speed that we wind up at. And we want to know how much energy was dissipated due to this friction process. So basically, we've got a kid on top of a slide. They slide like this. Actually, I'm going to just modify that. I don't want to give any indication of motion at the top. At the bottom, though, we do have motion. So we have our initial energy here and our final energy here, and we're going to set those equal to begin with. Now let's talk about what this means as far as the different types of energy that we have. So our initial energy is gravitational energy, and that gets converted into kinetic, and we have a little bit of dissipated energy or thermal energy at the end of the problem. So we begin with all mgh here because we have some height, and this becomes 1/2 mv squared at the bottom, and a little bit of E dissipated that's left over. So we don't have a formula for E dissipated, we're just going to see that it's left over from the other things that we do. So we have 24. I'll make g equal to 10 just to round it. Our height's 5 equals 1/2 times 24 times 2.8 squared. And we'll go ahead and solve for the E dissipated in that case. When we go ahead and do that, we're going to end up getting just calculating it out here. 24, well, 10 times 5, whoops. So we're getting about, the dissipated energy is going to be about 1100 joules. Okay. Now, if we have no friction, we want to know how fast the kid would be sliding. So I'll use a similar picture here, but now we have E initial and E final. Again, conservation of energy, but now all our gravitational energy gets converted only into kinetic. We don't dissipate any of it. So we have mgh equals 1/2 mv squared. Now notice, I'm going to do a bit of algebra here. I can cancel the m's on both sides through division. We'll have 2gh equals v squared, and then v is going to be the square root of 2gh, and now I can plug in my number. So I'll have 2 times 10, and my height's 5. When we actually simplify this, v is going to be equal to 10 meters per second. Awesome. Now, for question number 3. Here we're using elastic energy. So we notice at the beginning of this problem I have all elastic, and what happens is that the energy becomes gravitational and kinetic. So when we use conservation of energy, we're going to have E initial does equal E final. We'll have 1/2 k x squared gets converted into gravity energy and kinetic. You know what? I don't actually like how I wrote that. So we have E initial equals E final. And I want to first emphasize that we start off with all elastic, and that becomes gravitational and kinetic. There's none dissipated. Now I'll put in the letters. And, oops, sorry, that's 1/2 kx squared becomes gravitational and kinetic. And I'm just using the B's here because that's how they label the letters. Okay, so I have 1/2 times 1,000 times 0.6 squared equals 2 times 10 times my height, which is 5, plus 1/2 times 2 times v squared. So we're going to have 0.36 times 1,000. That's going to be 365. So I'm going to have 180 equals 100 plus v squared. And I'm getting 80 equals v squared. So v is going to be about 8.9. Let's just double check that. So yeah, about 8.9 meters per second. Awesome. Now, the problem that I gave you for homework on the lab, we want to know the speed that it can give to this ball. So we have initial energy still equaling final, but now we have elastic energy getting converted into kinetic. So we have 1/2 kx squared getting converted into 1/2 mv squared. Let me do a bit of simplification here. I'm going to multiply both sides by 2. So I'll have k, 850, times 0.4 squared equals 0.5 times v squared. So we'll go ahead and simplify all that. So 850 divided by 0.5 times 0.4 squared. And then we'll take the square root of this little dude. And so our answer works out to about 16.5 meters per second. Yep. So again, the idea here is that we have a spring that's compressed with a ball here. You know, I don't like how I do that. So here's a spring, and I'll put a ball here. And you know what I'll do is I'm going to actually compress a spring like that. And then what happens is that it'll stretch out, and the ball is going this way. All right. So that's problem 1 through 4 on the homework. Hopefully that will help you with all the stuff that's due for Friday.